So now we have some idea of how to predict the electronic states of simple molecules, and we should also understand that an electron donor is a molecule that has a high energy for its highest occupied molecular orbital relative to an acceptor which has a lower energy than this for its lowest unoccupied molecular orbital, so that the donor-acceptor pair can form respectively a cation and anion by transferring an electron from the donor to the acceptor. We haven't talked at all how immersion of these molecules into solvent affects the energy of the states and stabilizes the charged or neutral states of the molecules. And indeed, although these topics are the subject of intense theoretical activity and modeling, it's very hard indeed to get reasonable numbers from first principle models. Happily, chemistry has a wonderful experimental tool which is capable of determining in an absolute quantitative way the potential difference between the state of reactants consisting of a donor and an acceptor and the products consisting of a cation and an anion. This technique of electrochemistry is what we now turn our discussion to. So, if one were to just stick two metal electrodes into a beaker full of salt and apply a voltage, one would see something very much like this. The electrode that was positively charged would attract the negative ions from solution, which would accumulate on it with ever-increasing concentration to balance the positive surface charge on the electrode, and vice versa. The electrode that was negatively charged would similarly acquire a compensating layer of positive ions. Now, the fundamental problem that arises is this. All of the electric field, as we understand from when we discussed the Debye model of polarization at an electrode surface, is concentrated within about a Debye length of the electrode, which, as you now know, for a 1 molar salt is approximately 3 angstroms. Therefore, the electric field is dropped in 2 steps at this electrode and this electrode, which, if there are small currents in the electrolyte, then means there is effectively no electric field drop in the intervening liquid. Now, we know the total voltage V that we apply between these 2 electrodes, but we don't know the potential drop at any one electrode. Electrochemistry relies on a wonderful trick to quantify absolutely the potential drop at just one electrode. How is this done? It's done using an electrode that maintains a constant polarization as a reference electrode, shown over here. Now, in practice, the circuitry that might realize this might look something like this. So I'm asking you to remember the electronics you learnt in Chapter 4. So here is an operational amplifier with an inverting and non-inverting terminal. The non-inverting terminal is biased at some potential V with respect to ground. The inverting terminal is connected to the reference electrode that is immersed into the solution. The electrode of interest, the one at which the electrochemistry will occur, is grounded, and a third electrode inserted into this cell called a counter-electrode, and this is connected to the output of the operational amplifier. Now remember, with negative feedback, the reference electrode is connected to the inverting terminal, the operational amplifier will drive its output, i.e. this counter-electrode, to whatever potential is needed to make the voltage difference between these 2 terminals equal to 0. In other words, it will set the potential of the counter-electrode such that the potential difference between this electrode and the reference electrode is precisely V volts. In other words, if this were connected directly to ground, then the working electrode and the reference electrode would be at exactly the same potential. So, providing one has an electrode of constant polarization, which can be arranged by making the chemistry of the surface appropriate, and secondly, by making sure that the current that flows through it, i.e. the chemistry that occurs at its surface, is approximately zero, which is quite possible with a high impedance operational amplifier, one can then create a completely reproducible state of polarization at this working electrode. This is the key trick that makes electrochemistry work. Now, before we look at a practical electrochemical cell, we need to understand in the first place why ions would even go into solution. It costs energy to make an ion. This is the Coulomb energy, and it's shown here using an expression based on Coulomb's law in terms of E squared divided by the radius of the ion and the appropriate constants. This has to be compensated in some way. The thing that compensates this Coulomb energy required to separate, for example, a sodium and a chloride in solid sodium chloride comes from the increased entropy of the dissolved ions. And therefore one can write down, recalling the fact that the free energy of an ideal gas is given by the logarithm of its concentration, that kT times the log of the solubility of the ions exactly matches the enthalpy required to create these free ions, delta mu. So dissolution of ions then into, or an ionic solid, into a solvent occurs because of this entropy gain. Now, what happens when a metal is put in contact with an electrolyte? Well, even though the metal atoms are neutral in the metal and have to gain energy to become charged ions in solution, they also gain entropy. So there is a driving force for metal atoms to leave the surface as metal ions, donating an electron to the metal. This donation of an electron to the metal will raise the potential of the metal. The potential of the metal will continue to rise, atoms will continue to form ions in solution, until the point is reached where the Fermi energy, which moves upward in energy as the metal charges, exactly equals the chemical potential of the ions in solution. This means then that a metal electrode in equilibrium with a particular concentration of ions in solution has its Fermi level pinned at an absolute value with respect to the vacuum. This is how a reference electrode is made. The classic example is a platinum electrode in equilibrium with hydrogen ions in solution and hydrogen molecules absorbed on the surface of the platinum.